Hi, we are Project Kratos from Pilani, Goa campus, India. We are excited to showcase our latest rover, Kratos Mark II. Our team of 40 plus students have worked through multiple campus closures, online work sessions, and various restrictions to develop a new rover that is unique, modular, robust, and lightweight.
The mechanical subsystem works on designing, manufacturing, and improving the core rover, arm, and the life detection system. We have focused on improving our assembly using custom parts manufactured in-house. This year, we are continuing with aluminum box chassis, which houses our new electronics box and provides easy access to the electronics on board. We have improved on our previous double lambda rocker bug suspension with differential bar averaging for better performance over challenging terrain. The improved averaging mechanism helps the rover maintain ground contact at all times and reduces play in the assembly. Continuing with the 6-wheel differential drive mechanism, we are using 3D printed wheels with modified honeycomb support pattern, improving the shock absorbance. Grousers printed on the wheel provide grip on loose sand. The wheel design is optimized for faster and easy assembly. The modularity of wheels helps in faster replacement of parts in case of failure. The wheels, together with the suspension, help the rover climb steep slopes and even stairs.
We are using a combination of 2.4 GHz omnidirectional and sector antennas with a tested non-LOS range of 1 km. The rover is teleoperated using multiple camera feeds and a joystick from the base station. The required wheel velocities are computed using a differential drive model, which is then communicated to the motor drivers via raw serial. In case of connection loss with the base station, the rover uses the stereocam data to retrace its trajectory autonomously to reconnect.
We use a combination of lithium ion and live PO4 batteries with built-in BMS and cell balancing. The rover has been tested for 90 minutes of continuous traversal. The electronic box ensures the safety of all electronic components from voltage or current surges, dust, heat and vibrations. We use an emergency kill switch to shut down the entire rover immediately.
Our new 5 degree of freedom robotic arm is designed and tested for high torque and high precision requirements. The carbon fiber links and two linear actuators enable the arm to lift and drag payloads up to 5 kilograms while being lightweight. We have implemented a spur gear base rotation for better stability. For the equipment servicing mission, the actuators are controlled using inverse kinematics with a closed loop feedback system for easier teleoperation of the arm. The end effector is a two-jaw gripper with differential bevel gears to control its roll pitch motion, enabling the rover to perform tasks like flipping switches, pushing buttons, operating a joystick, and opening drawers.
For the autonomous mission, a state machine-based model is used for the navigation system. The entire autonomous module was first tested independently in the gazebo simulator before deployment on the onboard processor. For centimeter-level accurate rover positioning, a GPS module is used. The first 3 posts are traversed using optimal path planning. The point cloud generated by the Z stereo camera is converted to laser scan data, which is used to map the environment with obstacles onto a binary occupancy grid. The A-star search algorithm uses the grid for obstacle avoidance and efficient pathfinding to the checkpoints. The AR tags at the last 4 markers and gates are detected using the Aruco package of OpenCV. A spiral search algorithm is employed for searching the AR tags after reaching a checkpoint. Once an AR tag is detected, the rover moves towards it using a feedback-based visual servoing algorithm. Finally, reaching a gate or post is signaled using the integrated LED.
The rover can autonomously traverse various paths using a predictive Stanley controller, with the PID controller as a failsafe. The predictive Stanley controller has been thoroughly tested using simulations before deploying it on the rover.
The onboard science payload is able to retrieve up to 3 different soil samples for analysis. A ratchet wheel is used to collect soil samples and is partitioned in the collection bucket to prevent cross-contamination. Once collected, analysis is done through the live feed while traversing the rover to the next site, enabling us to complete the entire science task under 30 minutes. Extent life analysis is performed using a Bradford protein assay and a KMNO4 assay through a custom photospectrometer. The onboard lab has been tested to ensure no spillage of reagents or samples. We are using a custom imaging unit fitted with a PyCam and a neural net model to classify rocks to determine the extinct or no life conditions. Furthermore, to detect hypoliths and endoliths, we use red and green LEDs of various wavelengths and measure absorption to draw conclusions. Habitability estimations are performed by onboard atmospheric and soil sensors to assist our primary tests.
We annually conduct a summer program where we train over 150 students on various mechanical, electronics, autonomous and biology topics relevant to our project. We look to recruit the best performers in separate rounds. We regularly conduct demonstrations to increase interest in robotics and participation in projects.
Moving forward, we will be repeatedly testing the rover and demonstrating the competition tasks to find the limits of our rover. This has all been possible due to hard work of the team and support of our seniors and professors. We hope to see you at URC 2022.